So we are here again, now explaining point clouds, right? I hope that everyone has heard about point clouds, but if not, the definition is very intuitive, right? So we just have in this point cloud a bunch of points, and that's it, a set of points. Now, the peculiarity of this is that, at least for us, is that these point clouds, for instance, this one taking from an RGBD camera or this one taking from, well, a LiDAR, right, is that these are taking from okay, I think this is good. They are taking from an origin, right? So here you see like you have like some pose that is the pose of the sensor with respect to the world or some location. And this is where all these points are referred to, right? So most of them are just referred to this local frame, let's call it this way. The same happens here, right? So maybe we'll have like, yes, so this, in this case, this is kind of a camera, and maybe we have it here, okay? So point clouds are used also for defining maps, for representations in general, in graphics. There's many uses. For us, let's say that this is just the reading of some point clouds, right? That I mean, the point clouds are just readings of sensors, right? So sensors are giving information, and let's see how we can use the information. So one of the most straightforward ways of doing this is we get from these two poses a pair of point clouds, right? Like, let's say Z of I and Z of J. And the question is, okay, so you know that you have moved. You don't know what is the value of each of these two poses, right? But you know that there's a transformation that transforms all these points equally to the other points, right, on the point cloud. And well, broadly speaking, this is also called a registration problem or alignment problem. So what you are trying to do is just find like this transformation that makes the 2 point clouds coincident in the same reference frame of reference, right? Now, this has like 2 problems. The first one is, for this definition to be true, you need to sample exactly the same points. And imagine if you have here a LiDAR like this one, this is going to be very complicated. You move a little, you move like, I don't know, here, and who is telling you that this point here is going to be sampled exactly at the same position? Maybe something changed and then you got it here. So this assumption of having exact correspondence of the same sampling point, it's very unlikely. In fact, it's impossible, right? So in practice, yes, might be close, but sampling the same point, it's not possible. And then the second one is, well, noise. We didn't say anything about noise. So sensors are noisy, and that's why we do state estimation. So that's great. But this basically means that this definition is not that good. And the second one is, even if you have this perfect sampling, you need to know which point corresponds to which point, right? So this is called the correspondence problem. If you want also the data association of points, and here you have a lot of points, right? So it's not that trivial to have these correspondences. Okay, so this problem, if you can solve it, you can directly put it into pose-slam. This is going to be your observation, right? And this is how like things are related with respect to this rigid body transformation. So we know that this corresponds to a pose, and basically it's that, right? So we go with our robot like this, and then at some point we just say, hey, look, we are observing this, right? By this transformation from n to 1, right? So if you can calculate this, then you could be adding this directly to pose-slam. There's many other cases, right? You could be doing just this for mapping, right? So you want to aggregate all your point clouds into a single and well-defined map. This is another use. So now the question is, which methods are defined to solve this problem like a little more properly? I'm going to start with one of the simplest one and more direct ones because we don't have much time. I'm just going to go over it, but papers on this are in the readings folder in Canvas if you want to take a look. So because we don't have perfect correspondence now, what we are going to be defining is just an error function, right? It doesn't mean that they're exactly the same, but they should be close, right? If this is like points that correspond, in this case, K point corresponds to the, in the frame A corresponds to the point in frame K. And then this cost function, what it's telling is, okay, so you have all these points, you have calculated the correspondence. If you calculate the transformation, overall, that is the summation for all of them, should be small, right? And that's what you want to minimize. So on this method, the procedure for solving this equation, remember that this belongs to SE3, right? So we have discussed like some ways of solving this, but maybe there's others. What they did is they decoupled the problem in two parts. On the first one, they were just solving for translation, and this is based on this fact. So the centroids should be the same. If you have a point cloud, the centroid should be the same as in your other point cloud, right? And then if they are the same, the only thing that is going to be changing them once you calculate these two numbers is the translation vector. So this is an assumption, but it's reasonable if the scene doesn't change much. It's not so reasonable if, I don't know, you have only part of your point cloud, but still. And then on the second part, what they were doing is calculating rotation just with some SVD method, right? So they were creating a cross covariance of these observations, and the description on the paper, it's a little more detailed, but at the end, just by doing SVD of these cross covariance, they could obtain rotations, right? So that's good. It's a closed form method. It's fast. It's written here. It only requires 3 points in 3D, right? So this is the minimum number of correspondences you need to get a well-defined problem. If you have less, you will not solve it because you have basically not enough degrees of freedom. And what are other drawbacks of this, right? So if you add an outlier, this method is going to suffer a little. So when you calculate SVD, this is very sensitive to outliers. And the second thing is it requires correspondences. Okay, very quickly, we can formulate the same thing just as a minimization with respect to this rigid body transformation. So we have now our cost function. It's defined this way. We know what to do, right? So we basically can propose like this exponent update here, like this exponent update, and then with this gradient, we could be calculating things, right? So I'm not gonna go into the details, but each of these residuals is one of these differences, like vector transform minus vector in this target frame, right? Are they 0? We are good. Are not they 0? Then we need to reduce this. So this is the only thing that's doing. And here, what we are applying is the chain rule, right? So, okay, here we need 2, but fine. So how to calculate this? Well, in fact, this residual is just, we can put it this way, right? Instead of sets, we could be putting this. And does this residual resemble something? Yes, it resembles the vector transformation, right? So here we have kind of the same problem. We have a minus something that it's just going to disappear when we optimize, but on the residual it's going to stay. And then the derivative, it's going to be something like this: a skew symmetric matrix plus a term that depends on the identity. Again, this is just introduction. For now, it's going to be complicated for you to do these derivations, but if you take a look at the notes, I think that yes, you could be doing this after like some time of spending time. But at least you know under the hood what is happening. And this is actually what was happening also in the MROP example that I was giving you. I was just calculating derivatives not like this, but some of them were a little different. For instance, the landmark to pose, it was exactly this. because yes. Well, okay. Let's discuss about another very interesting method, which is RANSAC. This is not really only for point cloud alignment, but you could be using this for point cloud alignment, right? But it's more general. So the advantage of this is that it's adding robustness to the estimation, right? So RANSAC, it's kind of removing these inliers, these outliers from the inliers. We said that this was like one of the issues of SVD, also from optimization, right? So you need to take care of them. Optimization has other ways of taking care of them, by the way, but well, that would be for another day. And the algorithm is very simple, right? So let's start with this example of point cloud, right? You have a bunch of point clouds, a bunch of points in your point, well, let's call this X, and let's call this Y, right? So you have a bunch of them. The only thing you are doing at the beginning is just, we said that we need only 3 correspondences, right? So we are going to take this, this, and this. Why not, right? This is the minimum number of correspondences that we need. So we are going to be calling this subset S, right? So this is going to be our subset S. Now, what we do is we fit the model. In this case, we could be running the SVD method, right? The add-on, just with these 3 points. And this is going to fit the model saying, okay, look, so this is the transformation that you get from X to Y, right? Like, put it this way. The next thing is we are going to be evaluating which of these points actually like this solution, right? So there's going to be like this point. I don't know if it's assigned to this. So I'm not getting into the association right now, but this is also part of it, right? So this set of this random set could also be like trying different associations. So you could be then having like a more clear cost function later. So with this solution, we look for all points, all correspondences, if they fit or not, right? So for instance, if some of them is like very close and the error is small, you should be saying, yes, they fit. So you add them to the set of inliers. And if they don't fit, you classify them as outliers, right? And then basically the algorithm is just looking, look, is this set of inliers big enough? Then fine, we are done. We just calculate things with more information and that's it. If this set is not good enough, then we just repeat one. We sample again, right? We sample again like this initial set of inliers, and then we calculate this consensus set again, right? And at the end, well, we can return things. I mean, this is the standard original. There's many variants of this, by the way. But then at the end, what you return is which is the largest consensus set, right? So this is a nice way of handling outliers. Still, on the backbone, we are using a SVD method here just to calculate what is the transformation. But, well, things, let's say that just to add robustness, you need this kind of algorithms if it's not this similar. So very useful thing, RANSAC, probably you will be using this in other places for robust state estimation. Take a look later. And let's go now with the last slide. So this is also a very famous method, ICP. So ICP, what it does, it solves the problem of correspondence iteratively, right? So you have a point cloud alignment at the end, right? But the interesting thing is that a priori you don't have correspondences. So what do? We start with a greedy approach. That is, we just find the closest point, right? So we have a point, we calculate what is the minimum, what is the closest one, right? So here in this case, the example is this. You just calculate which is the closest one, and in this case, it's going to be this, right? And this is done for all points in this point cloud. It's a greedy approach, but still, it kind of works, and it has nice convergence properties. Basically, then we align, and here you could be using any method you want. And then we do this iteratively until convergence. So why we do this iteratively? Because maybe you move here, or maybe the solution is taking you here, right, to the next. So the point has been transformed to here. And then the closest point is not going to be this one anymore, but on the next iteration, it's going to be another point. And this changes the optimization. So that's why you need to do this iteratively. On this has been thousands of follow-up papers, many variants, many things, but still today, this is extensively used. So maybe some of you have like some of your projects involving point cloud alignment or 3D things. Starting point is ICP. There's many implementations of this, by the way, in modern, well, 3D libraries like Open3D, for instance. And I would say that, yes, this is an interesting method for you at least to know about, right? Because it's solving this correspondence problem that is very complicated, at least just taking a look at geometric features. Okay, there's nothing else for today. It was kind of, well, mixture of a little more of SE3 and this point cloud alignment. We'll be reviewing proposals, so you will get feedback soon, right? We are just checking in case that, there's like projects that are very hard to do, right? So we want to limit, but in principle, we gave you a lot of freedom. And if you want to discuss things with us now that, oh, we have this proposal, what do you think? We can change things. We're also open for this, right? So just arrange, if you want, like send us messages.